All right, great. So thank you all for coming today. It's my pleasure to welcome Professor Volker Deringer to the AI for Science seminar today. So Volker is a professor of materials chemistry at the University of Oxford, where he's been since 2019. And he trained in Aachen before getting his diploma and his doctorate, both there. Then he moved to Cambridge, where he was a Humboldt Fellow and later a Leverhulme Early Career Fellow. His work sits at the intersection of machine learning and material science, using computational approaches to understand the structure and properties of materials. So please join me to welcome him to today's seminar.
Yeah, thank you very much, Rocio, for the kind introduction, and to you and Simon for the invitation to come here. So it was a very quick decision when I saw the invitation to say, yes, absolutely. I've heard about this series before, and now I'm having a chance to come and visit and talk to people. And I've had some really exciting discussions already during the day. And I mentioned in one of them, it's actually, it's an interesting challenge, sort of how to set up the talk and what should I exactly talk about? Should I talk about methodology or about the applications of those methods? And I thought I would show a little bit of both. I would tell you a bit about what we're doing in our group. We're a group in the chemistry department at Oxford, and we specialize in materials with complicated structures. So materials that don't have nicely ordered crystal structures most of the time. And we then use machine learning methods to help us understand at the atomic scale what these materials look like. And I thought I would start with one example of a type of materials where atomistic modeling has long played an important role, and where machine learning methods have played a specifically important role over the years. So the material which is sketched here on the left is a germanium antimony tellurium compound, which is used in digital data storage. So it's called a phase change material for digital memories. You see here this fragment from the structure. It's very similar to a rock salt structure. You have octahedral environments. The structure is quite ordered. The materials are typically electrically conducting and reflective. And they can be switched into an amorphous structure, which is sketched here on the right. So amorphous means no crystalline long-range order. And you immediately see from this sketch here, the chemical environments are quite different. You have defective environments, you have some tetrahedra, which you don't get in the crystalline phase. And not only can you switch them from crystalline to amorphous, you can also switch them back using laser pulses or electrical heating. And so these materials have been used for many years to encode digital information, so ones and zeros, in optical disks, in electronic memories, and so on. And so these materials are really interesting from an application viewpoint, but also from a very fundamental chemistry viewpoint, because you want to understand what are the rules that determine what kind of local environments form and what is exactly happening there. So on the left here, I'm showing you a typical simulation that would have been done in this field, published a few years ago. This is an atomistic molecular dynamics simulation, MD. Right? So we compute forces on atoms and move the atoms according to these forces. And the process that's shown here is the crystallization of one of these GST materials, as they're called. So you start out with a mostly disordered phase. The atoms are color-coded red. They are amorphous. And then you see gradually how the crystalline phase grows from the upper and lower part of that model. So you gradually go from disordered to ordered over several 100,000 simulation time steps. The simulation on the left is done with a quantum mechanically based method, ab initio, or DFT-based molecular dynamics. The one on the right is run with one of these machine-learned potentials. I'm going to tell you more about how they work and what they do, but just looking at the structures for a moment, you see the process that they simulate does look very similar. They basically do a very similar thing, except that the calculation on the left took about half a year on a high-performance computing center, and the one on the right took a couple of days. So you see that that already really changes the speed and the type of problems we can study. And you also see, so this is a structure that contains just a bit more than 1,000 atoms. And a bit more than 1,000 is, I think, close to the limit of what you can do with first principles ab initio molecular dynamics at that stage. Right? You can't go much larger than that. But real applications often mean you need to go beyond that. So what is sketched in this cartoon here is one of these memory devices that people are looking at. They're called mushroom devices, which means there's a heater at the bottom, this bottom electrode contact. You see heat flowing through the bit of material here. It's crystalline initially, and then it gets melted near the heater. Okay, so this is why it's called mushroom-like. And you see here from a atom samples where we've got the crystalline phase with the more or less ordered structure. And then there's a region at the bottom where heat has been added to the system and it's been locally melted. You can go and look at temperature profiles. This looks a bit maybe like finite element simulation, but actually it is from a fully atomistic MD simulation. So we refer to this as device scale modeling, which means that you're looking at the length scales that are relevant to real devices. And then over the last years, of course, there's been many advances in how to run these simulations efficiently with even faster machine learning potential. So this is a recent example using a specific type of potential that is very fast to evaluate. So you see these sketches here of this, again, a mushroom type cell now going 100 nanometers across, which if you come from a atomistic simulation background, you think this is quite a large system to describe. You can now go, because these potentials are getting faster, you can not just describe the melting and the amorphization, but you can also look at the recrystallization. So you see the grain sort of appearing here in this cell, and you can test basically, for example, adding different amounts of heat gives you different types of what you could call logic states. So you see you can now do these kind of computational experiments where you simulate not just small and representative models, but much larger, much more realistic ones. And so I've got a very sort of bold claim, I think, at the top of the slide saying it has transformed materials modeling, but this is some of the evidence along many, many other examples, of course, how this has really changed that field. But to go one step back and say, what exactly are these tools and why do we need them, right? So the central task probably when you're running atomistic simulations is understanding what is sketched here as a cartoon, which is the potential energy surface, right? So you need to know the energy of a system as a function of where the atoms are. So if you're looking at elemental carbon, you would have maybe the diamond structure in a local minimum up here. You would have a carbon nanotube, it's maybe in a simulation cell like this. And these are systems that have been, of course, very successfully studied with first principles methods such as DFT for many years now. And so you see this nanotube here, it's a sheet of graphite which has been rolled up and put into this simulation box where it's periodic in the lateral direction, but then there's empty space that gives you the ability to describe this nanotube. But of course, if you then talk to experimentalists and say, you know, they're going to tell you, well, a real nanotube doesn't look exactly like this. It's got some defects, maybe. It's maybe has multiple shells. So you can quickly reach the point where you cannot describe this with quantum mechanics anymore. So the class of materials I'm talking about today are referred to as machine-learned interatomic potentials, which means that you're trying to learn that quantum mechanical potential energy surface. This is sketched here. So you're basically building a model that predicts energies and forces on atoms for much larger complex systems. You need 3 ingredients. That's the traditional way I would have talked about this. So you've got the first ingredient is your reference data, and that's actually something really important here on the left. So you need to choose at what points you do your quantum mechanical reference calculations. What structures do you choose? That's the one arrow. And then how do you label these things, or how do you compute your training data? Once you've got that, you need a way to represent the atomic structure and then, or featureize it if you want. And then you've got the regression task itself. So that's the machine learning model here sketched in blue. You see you have a few points. Those are the training data, but then you have the blue line approximating your true potential energy surface. It doesn't go through exactly through the dashed lines, but it's very close. And then with that model, you can go and run the types of simulations I've just shown you. More recently, I've actually sometimes gone and made the picture even a bit simpler and said there's two components here. There's the data that I use to train the model, and then there's the model itself. The cartoon here shows you the featurization, the architecture, all that together. And there have been tremendous advances, of course, in the architecture. So now you can fit, for example, graph-based interatomic potentials that are extremely accurate, very impressive. And there is, of course, still a lot of progress being made. But I do want to focus a bit on this side here and say, what about the training data? What kind of data do we actually use to train the models? And I want to structure this talk maybe using two different types of approaches that are a bit orthogonal almost. So one direction, I think, how do we make this really sort of easy to use and widely used is what I would call single purpose models. So you want a model for one specific purpose. And one important direction there is sort of taking existing molecular dynamic simulations, for example, speeding them up and getting single purpose models that are good for one specific type of problem. The other direction is really general models. So models that are trained on very large data sets that are applicable to many different problems. And I want to talk a bit about that later. But for now, focusing on the single-use models, what do we mean by that? So you can now take first principles molecular dynamics software and accelerate the process. So on the left here, you see the very simplified workflow for an ab initio molecular dynamics study, where you compute forces on atoms, you move atoms according to these forces, and then you go and do this many times over, and then you get your molecular dynamics trajectory. Now, what you can do instead of doing all of that from first principles directly, you could go and add acceleration from machine learning into that protocol. I'm showing you here a cartoon from a paper that describes the acceleration here for one of the DFT codes we work with CASTEP. This is not the first time this has been done. So this is done with other software as well. And I'd encourage you to look into also the literature and references here. So this is not, we're not claiming we're the first people to do this, but it is available in that code. You can use that to essentially accelerate your ab initio molecular dynamics directly. And I'm sketching this here with this cell here. This is a cell of about, I think, 200 atoms of carbon. In this case, it makes the simulation faster. But actually, you can go and use these approaches now and create new data sets. Right? So I've got in yellow these symbols for data sets or databases that you can then go and use to train standalone potentials that don't need the first principles code anymore, but they go and give you access to much larger systems. And I want to show you one example here. Right? So I want to show you a couple of the chemical systems we've been studying over recent years. And one of these systems is called graphene oxide. So you will have come across this kind of picture here. This is the structure of the perfect graphene, a honeycomb layer of carbon atoms. And sketched here on the right is something called graphene oxide. So it's actually a whole range of different types of environments you get in these materials. You synthesize them with quite sort of aggressive chemical reactions. They're very disordered structures you get. You make them over a long time, high temperature. And you see, if you're studying organic chemistry, you see a couple of sort of different organic functional groups essentially showing up in this cartoon. This is purely a cartoon drawn by hand. But these are the kind of functionalities you get in the material that have been experimentally seen. So what we now did is say, well, we can use the accelerated molecular dynamics. This is now this CASTEP plus ML, as it's called. We can use that to basically run DFT-based simulation speed them up with machine learning, collect data as we go. So whenever the model is too far away from DFT, we're going to add that to the training data set. And we can use that, and this is part of the DPhil work by Zach Machachi here, who finished his DPhil recently. And what's happening here is that, first of all, we're scanning over different parameters here. We're looking at different oxygen contents, different ratios of functional groups, initially for the two-dimensional sheets, but then also later on, we go to edge structures. We take sort of sheets of graphene oxide and look at what kind of functional groups might be on the edges. You see, initially, this is done with one type of model architecture. Later on, we switch to a different one, which is very expressive and able to then deal with these larger data sets and give us really very interesting simulations. So this is a common thing that you see in several studies from the groups, that sometimes we use different tools, different fitting architectures for different purposes to use their respective strengths. So you see here a plot of force errors over time as the model sort of gradually goes and learns about different types of structures. Initially two-dimensionals, learn quite quickly about 2D structures, but then once we start adding edge structures, it also learns about these type of edge functionalizations. You see there, you can make maps of these training data. So these are basically embeddings of the types of configurations that the model has learned. So you start on the left with lower temperature molecular dynamics, and then gradually we go up and explore more and more complex regions, and you see how that is gradually being added to the final data set. With that data set in hand, we now say, well, now we have a potential available. We can go and create these much larger structural models. For example, shown here, this is more than 10 nanometers on the side. So this is a sheet of graphene oxide, which has been annealed over sometimes. So you heat it, and then gradually the structure changes from a quite highly oxidized system. You see the plot here shows you how over time during the simulation, you lose water molecules, you lose CO2. So the structure changes and transforms and becomes a bit more graphene-like. You can track that change in structures in terms of the topology of the carbon network, but also you can actually go, because we have a fully atomistic simulation, you can go and count individual functional groups and look here, for example, at what's the amount of, here you see the direct bridging epoxides, basically in blue, going down very quickly as these get removed, and so on. So you can look into the microscopic details of what happens in your structure in a way that you cannot fully do experimentally. But you can go, and this is a very nice collaboration with Miguel Caro in Aalto in Finland, who in his group, they have developed a model that can predict X-ray photoelectron spectroscopy for carbon materials. So we could go and basically track how the different predicted spectra look as we take the material and anneal it. And then at the end, once you have done the annealing simulation, you can go and see it matches quite nicely with existing experimental data by others. So that's often, at the end, that's the real validation we need to make. We need to prove that our simulation is actually reliable in this way. It matches experimental data. With that kind of model in hand, once you know it is consistent with experiments, you can go and do various other things. Here's an example of mechanical properties of graphene oxide. So we're basically taking a graphene oxide sheet and then putting it under strain. You see here, basically it's being pulled in the direction of the arrows, and you see how then over time the sheet basically breaks. You can go and you can look at stress strain curves, and you can look at, again, the change in local structure. So what kind of functional groups are involved in this process of changing the structure up to the point that it just breaks. This is one example of course, many where you can say, now I have my model, it is validated, I can go and do basically computational experiments with it. The other part here, if you look on the right, what I've sketched here is the question about data sets. So how do we assemble for machine learned potentials? And one direction I want to discuss here is something that's implemented in a software we call Autoplex. So I'm going to show you a bit about the approach, the automation, but also I want to start with the ideas that are implemented there. So left, assume I want to explore a configurational space. So I want to, as I have a composition A, B, right, two types of atoms, but I don't know anything about the structure. I'm going to guess a lot of random structures and basically take them and relax them into local minima. So that's going from A to B. And if you take A and B in isolation, that is nothing new. That is a technique called ab initio random structure searching, invented by Chris Pickard and Richard Neitz, published back in 2006, so 2 decades ago. It's a very successful technique for predicting possible crystal structures. It was initially done with DFT. Right, so I could go and train machine learning potentials on those data. But actually what you can do, if you take all these 3 components together, right, you can use that exploration. You can not only go and sample structures in the first place, but you can go and build potentials that start to learn these things as you go along, use the potentials you have to search for new structures, add them to the model, and so on. So your initial potentials will not be very good, but they will know a little bit of the potential energy surface. And you go gradually and explore. You do all that using just basically single point DFT as labels, and you do all the exploration with your machine learned potentials. And we found that that's a quite efficient way to search for structures. Of course, initially, when you start thinking about these things, you write the tasks by hand and you code it up by hand and you run this quickly. But over time, you say you want to automate it. And this is a collaboration with Janine Georges' group in Berlin, who is an expert on automation for computational materials modeling, among other topics. And she has been extremely, I think, helpful also for us to understand what is needed to not just have Python code, but have a proper piece of software that is designed so that you can go and use it, and also hopefully other people. It's an ongoing collaboration. I'm sketching here in this cartoon basically how these workflow definitions look. Yes.
So in this workflow, you only use the minima for the next training set?
Good question. Not only. So we also take snapshots along the way where the structures get relaxed. And in fact, the first iteration has no minima, because so you do need to include higher energy regions, and these are really, really important. You need to train your model on things that would seem, as a chemist, they would seem very strange to you. So you're going to include structures. You look at them and say, this cannot be right, but you need to train the model so that it knows. Knows is a strange word. Show it where not to go. So here's examples. These are basically prediction errors for different. Sorry.
Even if you take snapshot on the way, you still have. Are you not having trouble getting the exact transition states, like the peaks, the rarest parts of the entire training surface? Are you not having trouble getting these right?
I think if the idea is sound enough, if you start with many random guesses, you're going to cover your configuration space quite widely. You might not get the exact most relevant point, but you tend to end up in the right minima over time. You're not aiming to get everything right. This is very important. You're aiming to get a robust model that you can start with, right?
For the simulations you're going to do with this afterwards, do you usually care about transition states? No, you care mostly about the stable states between the transitions.
Yes and no. So you do care about basically anything that you expect to come up, for example, in a molecular dynamics simulation. We wouldn't explicitly, transition states is a thing that we wouldn't be explicitly looking for here, but you're trying to cover quite widely low and high energy configuration. So what you're doing is now sort of measuring the error for a couple of standard test materials of stoichiometric titanium oxides, so not Pi102. With a number of DFT variations, the errors go down quite fast. 2,500 DFT evaluations sounds like a lot, but these are very small scale calculations so efficiently. If you have a large computing system, you can do these things probably in a matter of days. It is very efficient. You can do that. So here's an example where that can be useful. Because we only do single point calculations, we can run the searches with a relatively cheap functional, a GGA functional PBE here, but also we can use more expensive techniques. And the reason why I'm showing you this here, this is for silica polymorphs, is that actually with PBE, it's difficult to find the correct ground state structure. So that specific approach of GGA DFT would give you cristobalite, which is a metastable polymorph at ambient conditions, as more stable as quartz. So that's not the right way around. And you can see that if you go and track sort of how these searches go, you see the autoplex searches here with dotted with solid lines, sorry, and you see the dashed lines. That's the DFT, right? So if you train it at the incorrect level of theory for that purpose, it's going to faithfully give you the wrong result. Whereas here you use it with one that has the right energy ordering, you get the right result. So it's always about, of course, choosing the right approach for the right purpose. Okay, these were quite simple examples. What I'm showing you here is this one. We've seen this at the start, germanium, antimony, tellurium. So this is now a much more challenging system where indeed you can run molecular dynamics. And this is coming back to this point that you need to include some very non-equilibrium configurations, right? Black is ab initio molecular dynamics, red is the model from this automated run. You can say, well, the one on the left, we have potential for that we've had for years, so why do a new one? On the right, I'm showing you an example for a different phase change material, also used to store digital information. It has this kind of crystalline amorphous transition. It's less widely studied, of course, not used very widely as GST, but it is of interest. And you can say from scratch, you can come up with an ML potential model that can also describe this amorphous structure. And then finally, you've seen at the start this kind of crystallization of GST. This is what a model trained only on this iterative random search would produce for you. You see, it's not perfect. It crystallizes faster than the other model I've shown you, which is much more carefully handcrafted and tested. But it does get the basic ideas right at quite low computational expense. So I thought this was quite nice to see. A brief advertisement break here. So there's the QR code, of course, if you want to have a look. Please do have a look if you're interested in this kind of automation for ML potentials. Have a look at what the code does, and we're always very, I think I speak for all of us if we get maybe feedback from people and you tell us if you've used the community. Okay, so the last part of that cartoon here is something called model distillation. So what I'm sketching here is basically a generally applicable model, which has, you see, it's quite a large model, it's quite complex, it is very accurate, it's been trained on a large data set, but assume that this model is quite, so many different types of configurations. So what if I actually want to go and only study a specific problem, but much more quickly? So this is where this idea of model distillation is relevant. So you say you take a model and turn it into a cheaper one that cannot do everything, but it can do some things. And one approach I want to show you here is from a 2022 paper by Joe Morrow, who was a DPhil student with us at the time. So he said, well, you know, you train your ML potentials with basically your reference method. That's kind of the standard cartoon you would show. But with this model in hand, with this blue line that we have, we can now go and create much more training data, right? We're not limited to using the quantum mechanical method directly. We could go and say, well, let's create a second data set. So we call the first one D0, the second one is D1. That's labeled with that ML potential. So that's the and we create these configurations. You see in the cartoon here, we're not trying to cover everything. We're trying to cover this part here in the middle with many, many individual snapshots at that level. And then we go and fit a much faster model, we call M2, to those data, right? So you see, it's not expected to be great. Student model, so the teacher model is slow, but very accurate, relatively slow. We're using as teacher, we're using silicon gap 18, which is a very well established and extremely successful potential for silicon made by colleagues of mine. So I was not involved with developing the potential, so I can tell you it's really great. I'm used it for many, many things. But just based on the model architecture is relatively slow compared to other approaches. And so we said, well, can we distill this into a different type of method? In this case, moment tensor potentials that are much faster to run. And we're not trying to cover, as I said, the entire configuration space. So you see in blue here, these symbols is an embedding of the training data set of silicon gap 18. It has seen all sorts of configurations, bulk diamond, high pressure crystals, very high pressure regions, 2D structures, and so on. You see all these things here covered. The student model is meant to do only this part here at the bottom. So amorphous silicon and its changes under pressure and liquid configuration. So actually just the high pressure, I think not even liquid, just the high pressure amorphous under pressure. Anyway, there's a whole interesting story there. But that's the region where it has seen a lot of data. And just to, so if you're interested in the details, I'd refer you to that paper. But I wanted to show you two examples of what you can then do with these things when you have a very fast potential that you can evaluate cheaply. So one thing we've been looking at for a while actually is defects in amorphous silicon. Amorphous silicon is sort of the canonical, probably disordered inorganic material. Most of the atoms are tetrahedral, fourfold connected. A few atoms are not. So you've got these dangling bonds here in blue, or floating bonds, as people call it, so 5 neighbors. In particular have quite high energy, and they occur on the scale of maybe 1 or 2% in total. So we said, well, if you want to study these things, you need good statistics. You need a very large system. So we looked at a system of 1 million atoms of amorphous silicon. At about 6,500 threefold atoms, you get about almost 17,000 fivefolds. So you get, I think, quite meaningful distributions of these defects. You can now go and look at, for example, how the energy is correlated with the distance. You can look at the different types of environments you find. So this is a bit like sort of coordination environments in inorganic chemistry that you can find sketched here. And just having access to very large simulation cells at low cost, I think is really useful when you're studying things like amorphous materials. The other example is, so this is a different study by Louise Rosset, who is a current 4th year DPhil student in the group. So she's been looking at a topic that's been actually studied and debated in that field for a long time. Sort of, can there be some local structural order in amorphous silicon that has been referred to as paracrystalline ordering. So it's not crystalline, it's still a disordered network, but there is some local order. You see these kind of atomic environments here that locally resemble the ordered phases. And what she was now able to do is quite efficiently sort of build a large data set of lots and lots and lots of different amorphous silicon configurations. You see here in energy all the way from really disordered to much more ordered and even polycrystalline structures. And what you have here on the right is 100,000 atoms of amorphous silicon with some of these sort of small regions of local paracrystalline order. But so Louise could show that that model, even though it creates it has a little bit of local order, it does very well capture what we call here the first sharp and the second sharp diffraction peak. Those are essentially fingerprints of the ordering in the structure. So this is just a showcase of what you can do with these fast student potentials. And then some more recent work, this is on archive here. This is now sort of connecting maybe some of these ideas with the ideas of large pre-trained or sometimes called foundational interatomic potentials. So these are, of course, very popular at the moment. You can go and fit graph-based models on very large data sets containing lots and lots of configurations. And now increasingly common thing in the community, I think, is to go and take these pre-trained models, fine-tune them, so specialize them on a little bit of domain-specific data. So say you want to study one specific problem, you optimize the model for that specific purpose, and then that's giving you a fine-tuned model. Of course, that is still relatively expensive to run. So what John and Daniel here said when they were DPhils in the group, they said, well, what about using those models again to create lots of synthetic data, so these kind of data labeled with the teacher model, and then fitting models with a different architecture to those. And they do this in a very, I think, sort of the data set is built in a very efficient way. There's a whole protocol and actually code for doing that. So you can go and basically take these models. Let's take here as one example. These are just sort of examples of different architectures. You've got Maze MBC is a pre-trained model, which is very accurate, doing very well. This is for water configuration. So it's being fine-tuned on water configurations, gets a very good performance on predicting forces here in dark blue, bottom left. But it is comparably expensive to run compared to other architectures. So what they now did here is basically distilling this model into other types of architectures. Here are two different graph architectures that are, you see that would be the yellow would be sort of directly fitted models to those data. Red are the distilled models. You see them very slightly higher in energy, right? So they're not exactly as accurate as the teacher model, but they give you access to faster simulations. On the right, you see a type of model that is actually not based on these graph network architectures. It's the pacemaker approach, which lets us run even faster. So I think that is also a good trade-off. You can look at the different sort of cost and number of atoms you can reach, and you see here now, of course, you can reach much larger systems. The horizontal scale goes from 10 to the 2, 10 to the 3, about 1,000 atoms, all the way to 1 million in the same environment. And then a few just sort of showcase examples contributed by different, some group members, some collaborators. So this is metallic hydrogen by Shihab Ben Mahmoud, who is now in the materials department at Oxford. So this is really, I think, this is a stress test case maybe for these potentials. Very high, you see temperature 50,000 Kelvin. Porous amorphous silica here contributed by Louise. Again, looking at the sort of low density amorphous silica, methyl ammonium lead iodide by Bianca Paszka. And you've got here organic reaction. This is in collaboration with Veronica Yoroskova and Fernanda Duarte in organic chemistry at Oxford, who look at these organic reactions in explicit solvent. Here's an example of that. Just examples of what you can apply these ideas to. So just to, again, show this cartoon, I think there's really different directions in which you can think about sort of data for machine learning potentials. And I try to convince you that this is a quite interesting part of methods development, an interesting direction to look at. And I've separated it out into essentially single-use models on the left, speeding up ab initio MD, for example, for a specific purpose. And then on the right, we've got this whole idea of very large pre-trained models that can be taken, specialized, distilled, and so on. So just to summarize, really, I've told you about machine learning potentials. I am claiming here that if they've enabled a step change in materials modeling, they've been really, really influential. And the most exciting thing in my mind is going from quite simple models of reality. This is what, of course, computational chemistry has a very long and successful tradition of building simple representative models. But now we can go and simulate essentially the real thing. So very large systems that correspond directly to what you see in experiment. Then the oh, the animation here is the wrong way around, sorry. So I've talked about data as one of the sort of main directions, I think, in methods development in that field. Lots of interesting questions. And then I've shown you a few examples of amorphous materials, so disordered solids that we're interested in the group, going from fundamental questions such as the local order in amorphous silicon all the way to devices and practical questions such as the phase change materials I've shown at the start. So I would just like to say big thank you, obviously to all of you for your attention and for coming here today. I'd like to thank the group, of course, who are doing the work. This is a photo, I think, from last year, and several of the people in this photo have already moved on to new positions. So this is not the current setup, but this is sort of a snapshot from a while ago, and a few of the names who are underlined there, their work was featured here. The funders, thank you very much for making all the work possible. And then finally, want to leave with another sort of advertisement here for software. I've shown you Autoplex, joined with Janine Georges' group on automating the tasks for ML potential fitting. I also want to highlight GraphPS, written by John Gardner as part of his DPhil in the group, which is a tool to basically develop and work with graph-based interatomic potentials. So a big shout out to him as well. And yeah, with that, I'd like to say thank you again, and I'm looking forward to more discussions. Thank you.